So in this video here, I'm going to run through the answers to exercise 2 in chapter 5.1, which is all about writing the electron configuration of a number of different atoms. In order to be able to do this successfully, you need to know this information in this box here. In fact, this is actually all of the information that you need to know. If you know this, you should be able to do any problem that they give you. So you need to know the orbitals and you need to know the order in which they come. So it goes 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p. You're never going to go beyond 4p at A level, so this is all you need to know. As well as knowing the order, you need to know how many electrons you can put into each subshell. So anytime you've got an S, the maximum number of electrons you're going to be putting in there is 2 electrons because an S subshell only has 1 orbital. So S is always going to be 2. If you've got a P subshell, each P subshell contains 3 orbitals. Therefore, you've got 6 electrons in total in that P subshell because each orbital holds 2. So everywhere I've got P, I've got 6 electrons. That's the max that I can put in. And for a D subshell, each D subshell has 5 orbitals. Each orbital holds 2, meaning a D subshell in total can hold 10 electrons. The rules are the same as GCSE. You start with the lowest available energy orbital, and you don't move on to the next orbital until that orbital is full. So if we start here with fluorine, fluorine has got 9 electrons in total. I'm going to be starting with 1s. The 1s orbital can hold 2 electrons in total. Then I move on to 2s, and I put another 2 electrons in there. So I've got 4 drawn. I've got another 5 to go to give me 9. Into 2p, I can put 6 electrons in total. Okay. If I put all 6 in there, I would have 10 electrons. Fluorine's only got 9, which means I'll be putting 5 electrons into the 2p. 2, 4, 9 matches the atomic number of fluorine, and I've got the order correct, and I've got the right number of electrons in each orbital. Moving on to neon. Neon has got 10 electrons in total. Start with my 1s, put my 2 electrons in, move to 2s, put my 2 electrons in. 2p can hold 6 electrons in total. 2, 4, 10 electrons for neon. Just remembered now, I'm pretty sure in this I asked you to draw out the p orbitals in full, so I'm just going to do that. So because I asked you to draw out the p orbitals in full, there are 3 p orbitals. There's a px, a py, and a pz. Same below, I'm going to be drawing 2px, 2py, and 2pz. I've got 5 electrons in total. I'll have 2 in px, 2 in py, 1 in pz. For neon, I've got 6 electrons, which means each of my p orbitals is going to be full. Your orbitals, when they are equivalent in energy, do fill singly before filling in pairs, meaning when I'm putting the electrons into these p orbitals, I would have gone px, py, pz, then went back and put another one in px and another one in py to give my 5 electrons in total. Same with neon, I would have gone x, y, z, still had 3 electrons to go, so I went back and did x, y, z again. Typically, at A level, you're not going to be asked to write your electron configuration showing the individual p orbitals. When they want you to demonstrate that you know they fill singly rather than in pairs, they use what's called the electron in box model. And questions of that type are already in the booklet. When you're asked to write electron configuration, they typically allow you to just put all of those p subshells together, which is what I asked you to do in question number 2. So now for question number 2, I've got sodium, 11 electrons in total, 1s2, 2s2, 2p6. That gives me 10 electrons. After 2p6, the next one is 3s. Where my remaining electron can go in to 3s. Magnesium has got 12 electrons, 1s2, 2s2, 2p6, just like sodium. That gives me 10. I've another 2 electrons to go. The s orbital can hold 2 electrons, so there's my 12. Aluminium has got 13, 1s2, 2s2, 2p6, 3s2. That gives me 12. The s is full. After the s, I move from 3s to 3p. My remaining electron can go in there, 3p1. Silicon's got 14, 1s2, 2s2, 2p6. So again, there's my 10. I've got another 4 to go. 3s2, 3p2. That gives me 14 in total. So when you've done these, quickly just add up your numbers, make sure they match the atomic number. That should add up to 11, to 12, to 13, and to 14. And you can see, because these elements are in order, that I'm just filling an extra electron in each time. So 3s1, 3s2. Then the 2 is full, I'm moving to 3p. But 3p1, 3p2. After silicon, it's phosphorus. So if I had given you phosphorus to do, it would have been 3p3. Then you move on to sulfur, it would have been 3p4, and so on. But instead, I asked you to do manganese, which has 25 electrons in total. So I'm going to start off as before: 1s2, 2s2, 2p6. So that's 10 drawn. I've got another 15 to go. 3s2, 3p6. Okay? After 3p, so I've got 18 electrons drawn now at this stage, but I need to draw 25, so I know another 7 to go. So after 3p, I've got 3d and I've got 4s. So I'm going to write down my 3d and my 4s. And it is common convention to write 3d before 4s, even though 4s is lower than energy, and even though 4s fills first. Now, if you wrote it the other way around, that is fine. It's correct. You'll get your marks. It's just common convention to put the 3's together and then the 4. So we've got 25 electrons in total. I've already accounted for 18. I've got another 7 to go. 4s is lower in energy than 3d. Therefore, I'm going to put 2 electrons into 4s before filling 3d. That leaves me with 5 electrons in 3d, and that gives me 25 in total. If I do iron next, iron has got 26 electrons, so similar to manganese. 1s2, 2s2, 2p6, 3s2, 3p6. So there's my first 18 drawn. I've got another 8 to go. As above, I'm going to write my 3d and then my 4s. I'm going to fill my 4s first by putting 2 in there. That leaves me with another 6 electrons, which go in my 3d. And again, if I add up all of these numbers, I will end up with 26. Next up, I've given you zinc. Zinc has got 30 electrons in total. So I'm going to write the first few again really quickly. Up as far as 18, I've got another 12 to go. So I'm going to write 3d, I'm going to write 4s. I've got another 12 to go. I put 2 electrons in 4s because it fills first, leaving me with 10 electrons to go into 3d. Okay, your d can hold 10 electrons in total. Okay, so there is my 30 electrons all accounted for. And then after zinc, I do bromine, which has got 35 electrons, so an extra 5 electrons. So it's going to be the same as zinc above it, but I now need an extra 5 electrons. So I need something beyond 4s. So beyond 4s, I've got 4p. 4p can hold 6 electrons in total. I only have 5, so I'm putting 5 electrons there in 4p. And again, I'm going to add those up at the end. I'm going to make sure it adds up to 35. There's another simple check that you can do to make sure you're right, and that is looking at your electron configuration and making sure it matches the position of that element on your periodic table. So I'll show you what I mean. Group 1 and 2 are called the S block elements. The transition metals here are the D block elements, and then you have got your P block elements from groups 3 to 0. If you're a P block element, your highest occupied orbital should be a P orbital. If we look at our P block, okay, so aluminium would count as a P block. It's in group 3. Highest occupied orbital is 3p1. Silicon's also a P block. Highest occupied is 3p2. Bromine here in group 7 is also a P block. When I wrote out bromine, I saw my highest occupied was 4p. So they're all fitting that pattern. Any of my D blocks, their highest occupied orbital should be a D orbital. So here, manganese, iron, zinc, they're all D block orbitals. Now, yes, we filled the 4s first, but that's because the 3d was higher in energy. Therefore, our highest occupied energy level is going to be our 3d. Okay, so they are D block elements because the last electron went into that D orbital. And then you've got your S block elements, so sodium and magnesium. their highest occupied energy level is an S block. So that's just a quick check to make sure that you've done it right. Another quick check you can do is just by using the period that the element is in. So for example, sodium is in period 1, 2, 3. Therefore, it should have 3 different energy levels. It's got a 1, a 2, and a 3. So it does have 3 different energy levels. Bromine down here is in period 1, 2, 3, 4 for bromine. Therefore, you should have 4 energy levels. I've got a 1, a 2, a 3, and a 4. So that's correct. If I take one of my transition elements, so iron is also in period 1, 2, 3, 4. So again, there should be 4 different energy levels there for iron. And I've got a 1, a 2, a 3, and I do have that 4s. So I do have 4 different energy levels for my period 4 element. So they're just quick checks relating your electron configuration back to the periodic table to make sure that you are correct. Because it can be a bit tedious writing out electron configuration, I mean, you can see above that I've just been writing the same thing over and over and over. There is a shortcut that exists. Now, to be fair, you're not typically asked to use this shortcut at A level. They could include it in a question and expect you to know what it means, but typically when they ask you to write the electron configuration for yourself, they don't ask you to use the shortcut, but we're going to go through it anyway. So what you do is you use the noble gas configuration. So if I ask you for phosphorus, phosphorus is here in period 3. You go to the period above and you go to the noble gas in the period above, which is neon. So I'm going to put neon in square brackets. And neon has got 10 electrons. So by putting neon in square brackets, I've accounted for the electron configuration of the first 10 electrons. In other words, the 1s, the 2s, and the 2p. Instead of writing that out, I just write neon in square brackets. Phosphorus has got 15 electrons. 10 are already accounted for, meaning I've only got another 5 to go. So where are you going to start then? Where do you pick up your electron configuration? Well, phosphorus is in period 1, 2, 3. So I'm going to be starting with the 3rd energy level, and the 3rd energy level starts here with 3s. So for phosphorus, I'm just going to write neon, and then I'm going to pick up with 3s. I've got another 5 electrons to go. Neon represents 10. Phosphorus has got 15 in total, so I'll put 2 in the 3s, and then I've got 3 left to go into my 3p. So neon is just representing this 1s, 2s, 2p6, those first 10 electrons, and the other 5 I write out in full. Chlorine is going to be the exact same story. Chlorine is also in period 3. The noble gas in the period above is neon. So I write neon to represent the first 10 electrons of chlorine. I've got another 7 electrons to go. Again, because chlorine is in period 3, I pick up with the 3rd energy level, which starts with the 3s2. And I'm going to have 3p5. So I've got 2 and 3 is 5, and 10 is 15. 2 and 5 is 7, and 10 is 17. With potassium, potassium is down here in period 4, so I'm going to period 3, and the noble gas in period 3 is argon, and argon accounts for the first 18 electrons, so I put argon in a square bracket. So again, instead of writing out the 1s2, the 2s2, the 2p6, the 3, all of this, okay, as far as 3p6, the first 18 electrons, I can just put argon in square brackets already. Potassium's only got 19 electrons, 18 are represented by argon, so I've only got 1 more electron to go. In order to know where to put it, I look at my periodic table. Potassium is in period 4, 1, 2, 3, 4, so it's in period 4. So period 4 is going to start off the 4th energy level, and that's going to be your 4s. So 4s1. Calcium is going to be the same. It's next to potassium, but it's got 20 electrons. So argon represents the first 18. The last 2 will go into your 4s orbital, 4s2. Scandium is next to calcium, 21. So I'm also going to be using argon as my noble gas. Got 21 electrons. You can see here it's a D block element. Okay, so I'm going to need to include my 3D as well as my 4s. Okay, so remember the argon accounts for all of this bit. It accounts for the first 18 electrons, but it doesn't account for the 3D or the 4s. For potassium and calcium, I didn't need the 3D because the s orbital was enough. But for scandium, I need to show my 3D and my 4s. I've got 3 electrons left to assign because argon represents the first 18. I put 2 in my S, I put 1 in my D because S fills first. Titanium, I'm going to do the same. Titanium is next to scandium, it's got 22 electrons. So I'll need my 3D, I need my 4S. I've got another 4 electrons to assign because 18 are accounted for by argon. I go 2 and I go 2. Vanadium is 23. So I go my argon, I go my 3D, my 4S, I go 2 and I go 3. So there's an extra 5 electrons as well as the 18 accounted for by argon, giving me 23 in total. Okay, so it's a shorthand. Again, you're not typically asked to write your electron configuration in this manner because they want you to show all of the individual subshells, but it is important that you know what this type of notation means.